Okay, let's get started. My name is Han-Bong Lee from NASA Ames, and I am the Systems Analysis Lead in the ATD-2 project. And today, the session title is Simulation and Modeling used in Surface Analysis. But today, I will focus on the phase-time simulation model applied to the surface operation modeling and analysis used in the ATD-2 project. So here's the outline for today's presentation. So I will briefly review the phase-time simulation in the ATM field, and then I will show the two case studies using the phase-time simulation in the ATD-2 project. The first one is the impact of the UVT quality. I will present this case study, and then the Dr. Aditya Saraf from ATEC, our co-moderator in this session, will present another case study, the ATD-2 benefit assessments using the phase-time simulation. So the phase-time simulation can be used to evaluate the current and future concept of operation in the air traffic management field. So actually for the concept evaluation, we can think of the three different methods: the phase-time simulation, and human-in-the-loop simulation, and the field demonstration. So usually the human-in-the-loop simulation and the field demonstration are so expensive, and they require lots of efforts to implement. The human factor also affect the simulation result. So compared to them, the phase-time simulation is an efficient and cost-effective method for the concept evaluation. And on the desktop, we can repeat the same simulation multiple times without any concern on the fatigue or workload from the human beings. And then we can just focus on the specific research question by setting up all the other conditions are equal in the same. And then we can also visualize the simulation result easily. However, we have to validate the simulation model and the parameter used in the simulation to make sure all the simulation represent the actual operation correctly. So there are lots of examples for the phase-time simulation tool, including the CMOD, TAAM, AirTop, and SOS. But today, I will focus on the last one, the SOS. So basically, SOS, the Surface Operation Simulator and Scheduler, was developed by NASA for the airport surface operation modeling. So this is based on the node-link model for the airport surface, and this tool can be used to develop, analyze, test the concept of operation for the airport surface traffic management, as well as the runway scheduling algorithm. So this figure shows the screenshot from the SOS simulation model for the Charlotte International Airport, and you can check this website to get more detailed information about SOS. So we see a lot of potential application from SOS. First of all, we used our SOS model to assess the benefit of the surface metering in the ATD-2 concept. So we applied the SOS model to assess of the benefit from the surface metering to the multiple airports in the US, including the Charlotte Airport, DFW, and New York Airport. The Aditya will present about that. And we also applied the same surface metering concept to the other international airports in the foreign countries, such as the Hamburg Airport in Germany and the Incheon International Airport in South Korea. And we also evaluated the impact of the UVT uncertainty, the estimated flight ready time uncertainty on the surface metering. So I will present about that later. And we are now currently looking at the impact of the general aviation flights on the surface airport's performance. Yesterday, Craig from MITRE presented about the opportunity for the mobile application to send the UVT from the general aviation and business jet pilots. And so from source, we can evaluate how the schedule can be improved by this new input about the UVT from the general aviation on the surface scheduling. And we are also collaborating with KARI, the Korean Aerospace Research Institute in South Korea, to develop the de-icing operation model during the winter season for the Incheon International Airport. And SOS also has some function to model the various uncertainties in the surface operation, including the pushback process time, the aircraft taxi speed, and runway separation time, and so on. So we can evaluate the effect of these uncertainties on the airport performance. And there are lots of other potential applications. So I want to take some your input about the potential from the FaceTime simulation. So now I will talk about the case study number 1. So this is about the evaluation of the impact of the UVT, the estimated flight ready time uncertainty on the surface metering. And this research work is will be presented in the DAS conference, the Digital Aviation System Conference in San Diego next week. So basically, we talk about the surface metering in this workshop because the surface metering is one of capability in our ATD-2 systems. So the surface metering can be applied for the efficient airport operation at the busy airport. And so basic concept of surface metering is to shift the wait time in the departure queue to the gauge to reduce the excess taxi-out time and save the fuel burn and the gas emissions. So yesterday, Jeremy already talked about the benefit of the surface metering applied to the Charlotte International Airport. So this surface metering can be implemented by using the tactical surface scheduler. So basically, the tactical surface scheduler calculates the target takeoff time of departures, considering the unimpeded takeoff time and the operational constraints like the runway separation time for the wake turbulence. And then provide the pushback advisory to the ramp controller to hold some departures to reduce the surface congestion. So to calculate this target takeoff time and the target off-block time, we are using lots of input data, including the flight plan data, estimate flight ready time, taxi time prediction, various TMI restriction for the traffic flow management, and surface surveillance data, and so on. But we will focus on the estimate flight ready time because the estimate flight ready time and the taxi time prediction will be used to compute the unimpeded takeoff time. So this estimate flight ready time will be called as the EOBT, the earliest off-block time. I think you guys already had heard about the EOBT a lot in this workshop. So basically, the EOBT values are provided by airlines based on their flight readiness status, including the turnaround time at the gate, the passenger boarding progress, and the baggage loading rate. So this EOBT value will be used as the one main input for the tactical surface scheduler, as I mentioned. So the accuracy of EOBT is one important factor to determine the surface scheduler performance. So the airlines keep trying to improve their EOBT accuracy for their flight planning and operation. But the EOBT data is not exactly as same as the actual off-block time. Sometimes the EOBT is far from the actual pushback time because of lots of uncertainties related to the flight operations. But we want to know how the EOBT accuracy can impact on the surface metering and the airport performance. but it is very challenging to see the direct impact of UVT accuracy on the scheduling in the real operation because of lots of factors affecting the actual flight operation. So as an alternative method, we can use the phase time simulation to see this impact. So here are my research objectives. First, we developed an UVT model to represent the actual characteristic of the actual UVT data patterns. And then we integrated our phase time simulation model source with this UVT model and the ATD-2 tactical scheduler. And then we evaluated the impact of UVT accuracy on the airport performance and the benefit of the surface metering using this phase time simulation platform. So first, I will describe how we developed the UVT quality model. So as the data source, we used the 1 week flight data at the Charlotte International Airport in February 2018. After the data filtering, we got around 2,300 flights, and the UVT updates are around 3,800 in this sample. And then to characterize the UVT data patterns, we consider the 3 major variables, which are the UVT update time and number of UVT updates and the UVT accuracy, which is the difference between actual pushback time and estimated flight ready time. So from these key 3 variables, we can define when the UVT data will be updated and how many times the UVT will be updated, and how accurately airline can predict their flight ready time. So this chart shows the UVT accuracy with the updated sequence at the Charlotte Airport. So this flight is for all the departures regardless of any airlines. And x-axis shows the look-ahead time before actual pushback within the 30-minute time window. And y-axis shows the UVT accuracy, the AOVT minus UVT. And we need to keep in mind the 3 main key elements, which are the UVT update time, update frequency, and the UVT accuracy in this chart. So in this graph, each line shows each line shows the sequence of UVT updates, the multiple UVT updates. Some circles like these are showing the flights having one single update during until the pushback. So yes, many flights just update their UVT just one time before pushback. And in this chart, you can see that there's a trend about the UVT accuracy becomes a negative value when the time is close to the actual pushback. That means the UVT is become later than the actual flight ready time because the airline want to put some buffer time in their UVT value to consider some uncertainties related to the flight operations. Okay, so from this UVT data observation, we developed the UVT model using the 2-step approaches. So in the step 1, we define the number of UVT updates for each flight and determine the time when the UVT will be updated. And in the step 2, we model the UVT accuracy at each updated time. So in this model, we assume that the UVT accuracy is following the normal distribution with the 0 mean at each time being within the 30-minute time window up to the actual pushback time. And then we estimate a single sigma value for all the required time being. So from this approach, we developed a linear regression model for the UVT accuracy, like this formula. So the y shows the UVT accuracy, and xk shows the UVT update time with the number of UVT updates. And we also put the sigma value to represent the distribution of the UVT accuracy at each point. So by adjusting these parameters and coefficients, we can generate a new data set of the UVT data, the mimicking to the actual UVT data. So to validate the UVT model, we also look at the 1 week flight data at the Charlotte airport. And from the 1 week data, we found out the UVT update frequency is about 1.65 for each flight. That means the most flights just update the UVT value once or twice up to the actual pushback. And the sigma value for the UVT accuracy model was about 3 minutes. And we also found the coefficient fitted to the actual data, like these values. So from these parameters, we could generate a new data set of the UVT distribution like this on the right-hand side in the green dots. And the left-hand graph shows the actual UVT data distribution. So you can see that these two scatter plots look similar. Okay, then I will describe how we set up our fast-time simulation platform. So this chart shows the data flow between our simulation engine source and our ATD-2 tactical surface scheduler. So in the middle of the chart, we have a surface modeling module to exchange the data between source and the tactical scheduler. And this module also received the UVT data from the actual UVT model we developed. And after running the simulation, all the simulation output will be archived in the database for the post-analysis. And for the simulation scenarios, we chose the 4 different days having the heavy traffic demand at the Charlotte airport for the 2 hours in the morning time. And all these 4 different days are under the south flow configuration, having the 2 parallel departure runways, the 18 center and 18 left. And this table shows each scenario date with the number of departures and arrivals. So in each day, we have around 90 departures and 90 arrivals within the 2-hour time window. And then we validated our simulation model to make sure our simulation model represents the actual operation. So we compared the simulation output with the actual operation data in terms of various performance metrics, but I will skip the details here. So now I will talk about the evaluation of the UVT accuracy impact using the fast-time simulation tool. So for the simulation setup, we are using the same 4 scenarios from the Charlotte airport. But in this scenario, we just use the fixed target access text time parameter in the scheduler. So from the previous research, we found out that this target access queue time parameter can determine the gate holding time and text time reduction. But and usually, as the target access queue time parameter is set to the smaller value, then we keep the smaller size of the departure queue, and more departures can be held at the gate. But to exclude the impact of this parameter, we are using the queue parameter in our simulation. And we just focused on the impact of the UVT accuracy. So we set up the 4 different UVT configurations having the different level of UVT accuracy. And these UVT values are controlled by the UVT model we developed. And then we ran 20 runs with the perturbated flight ready time in the simulation. So in total, we had 320 runs for the data collection, and then measured the different performance metrics, including the gate hold, takeout time or departure, takeoff delay, target takeoff time predictability. So I will talk about the UVT configuration in more details. So we tested 4 different cases having the different level of UVT accuracy. The first one is the sigma 0 case. The sigma value is 0, and this means the perfect UVT case. So in this case, all the UVT values are exactly same as the actual flight ready time. And the second one is the sigma 3 case, which is the baseline because this data came from the actual 1 week data at Charlotte Airport. And then we adjusted the sigma value like the sigma 1 and sigma 5. So in the sigma 1 case, we can see a little better UVT accuracy. But in the sigma 5, we have large variations in the UVT distributions. So from our simulation output, we measured the different performance metrics. The first one is the number of metered departure, the number of metered flights. So in each scenario, we look at the number of metered flights, but those numbers are almost constant. So because we are using the target XSQ parameter in the scheduler. And then we also look at the gate hold time, the difference between the target off-flag time and the actual flight ready time. And this graph shows the mean overall gate hold time in minutes for all the departures in the scenario. And in each scenario, the first bar in purple color shows the sigma 0 case. So with the perfect UVT values, we still have some gate holding time because of the heavy traffic demand in the scenario. And as the UVT level increases, UVT uncertainty increases, then we see the gate holding time is also increases because of the uncertainty on the UVT data. So usually in the scheduler, the target of flag time is dependent on the UVT, especially when the UVT is later than the actual flight ready time. Then in that case, the scheduler set up the target of flag time to be same as the UVT. So the UVT is too late, then that flight will be held at the gate until the UVT value provided by the carrier. So that's why we have long gate holding with the UVT uncertainties like this. Okay, so this additional gate hold just induced by the UVT uncertainty. But when the UVT is too early, on the other hand, then that flight will be hovering on the scheduler timeline because the flight is not ready to push back yet. So at some point, the scheduler will wait and then send back to the uncertain group for this flight. Then this change can induce additional gate holding for that flight as well. So the UVT uncertainty can increase the gate holding time unnecessarily. And then we look at the mean takes time reduction by gate holding compared to the no surface metering case. So for this comparison, we just compared the actual takeoff times between the surface metering on and off cases. So this graph shows the mean takes out time reduction for each UVT accuracy. And you can see that the surface metering does reduce the takes out time around ranging 0.8 minute to 1.6 minute, depending on the scenario. But sometimes in a few scenarios, like the blue curve and red curve, the takes time reduction was increased because of the additional gate holding time. So usually, sometimes this additional gate holding time can have the reduce the takes time, which is very interesting. But when we have a long gate holding due to the UVT uncertainty, then this flight will be held for a long time at the gate, and then when the flight is actually pushing back by following the TOVT, then at the time the the surface congestion is already mitigated and the peak time is already passed by. So there's no lots of traffic on the surface at the time, then they can get a little shorter taxi time. But this is not the situation that the airline want to have. And we can have about concern about the takeoff delay for the metered flight, because those flights will be held at the gate for a while. But this red color shows the takeoff delay of the metered flights, and aggregated takeoff delay from 4 different scenarios. But as you can see, the takeoff delay is not affected by the UVT accuracy. So actually, the takeoff delay is mainly determined by the traffic demand itself. And from the statistical analysis, we see no significant relationship between gate holding and the takeoff delay. So in the sigma 5 case, the additional gate holding just translates to the taxi time reduction, as I mentioned in the previous slide. So that's why we have a similar level of takeoff delay, regardless of the UVT accuracy. And we also look at the target takeoff time predictability. So we measure the target takeoff time compliance, which is the difference between the actual takeoff time and the target takeoff time from the scheduler. But the median value of the TTOT compliance was similar regardless of UVT uncertainty, but we just measured the standard deviation of these TTOT compliance. And this graph shows the standard deviation of TTOT compliance. And we see the better UVT quality shows the smaller standard deviation of the TTOT compliance. That means the better UVT quality can help the scheduler predict their target takeoff time more accurately close to the actual takeoff times. So that means we can increase the confidence about our scheduler output with the better UVT accuracy. And then with this reliability, we can reduce the target excess queue time in the scheduler to have more gate holding and taxi time reduction. Okay, so in summary, we developed the UVT model based on the linear regression model from the actual UVT data, and then this model was integrated with the phase time simulation platform. And then from the phase time simulation, we see that the UVT uncertainty can increase the gate holding time unnecessarily, and sometimes those additional gate holding can reduce the taxi out time depending on the scenario. But there is no big impact on the takeoff delay, and this UVT uncertainty will lower the scheduler's takeoff time predictability as well. And this afternoon, the Tom Reynolds from MIT Lincoln Lab will talk about more details about the benefit of the UVT quality. So this is my presentation, and I will take some questions from audience.
I don't see any questions from the online booth. Yeah, are there any questions in the room?
Seems like introducing some simulated uncertainty would increase the amount that they spend in the gate and therefore reduce fuel consumption.
Yeah, it's possible. Yeah, it's very interesting, to me. But as I mentioned, we just fixed the target excess taxi time parameter in the scheduler, and just look at the impact of the UVT accuracy. So sometimes, depending on the traffic scenario, we see some fuel saving from the UVT uncertainty, but it's ridiculous because they hold the departures at the gate too long, more than 10 minutes. That is not good for the airline's operations. Yeah. It's possible. Yeah, it's very interesting. Yeah.
Is it relevant to look at the throughput as well? I know you're looking at other metrics that are quite related to it, but I wonder if you have more
Yeah, that's a good point. Yeah. Balaji mentioned about the running throughput effect and the number of departures in the departure queue. But we also measured those metrics as well, but there's no big differences in the running throughput curve or the surface counts on the departure queue regardless of the UVT uncertainty, because we are using the target queue access time parameter, then we keep the same level of the queue size in the movement area. So there's no big difference. Okay.
Just one question. Were there any assumptions that you made for the data to fit the model, or just to get your results?
The question is about the additional assumption in the FaceTime simulation. So basically, the FaceTime simulation have lots of assumptions. For example, we just sent out the actual push. We just push back the departures exactly the same as the target of flight time, but in the real world, there's some differences on the target of flight time and actual of flight time. But we just ignore the difference in the simulation. Okay.
Was there a way of, maybe from the conclusions that you saw in terms of the research, a way of also trying to correlate the actual off-flight time and correlate that to the taxi time and the takeoff time? Meaning, one of the problems I'm assuming you're trying to solve is minimizing the fuel consumption of taxi, minimizing the time of taxi to the actual takeoff. Was there a way to do that with the data that you had? Or is that one a potential next step with regard to the analysis?
Yeah, so the question is about from our current result, what's the next step about? From our FaceTime simulation, we can compare exactly same condition with the surface metering on and off. So for the specific individual flight, we can compare how the text time changes from the metering and depending on the UVT accuracy. So as the next step, we will look at the deeper side for the individual flight level to see the effect of the UVT accuracy on the text time and gate holding time as well. Yeah. Thank you. Okay.
Dave Moore. Broader question, but is there any concern that there's going to be limitations on how good we can get EOVTs? And given what I saw with your variants, and that we're trying to do APREX, we're trying to do IDAC, we're trying to get people in the right spot to get into overhead streams, and that's requiring a very tight window of when they need to leave, and you've got EOVT accuracy much greater. Is there a look into how good we can actually get and what we can expect in the future, where we're trying to meet APREX? Aditya is going to talk next, but we're looking at in data where APREX actually are in the wrong place. They're too early, and when they stop, and sometimes they block people behind them, and it does affect departure throughput. What's the thinking there?
So currently in this simulation, we just ignore the effect of the TMI constant, like the APREC flight or CFI flight. So we just assume there's no APREC flight in our scenario. But definitely they also affect the performance on the scheduler. So we also need to include them in our FaceTime simulation, but there's some limitation in the capability of our simulation tools. Yeah. Okay, then I will hand over to the ITR to represent the second case.
Okay. Thanks, Anwar. Thanks, everybody. My name is Aditya Saraf. I'm going to talk about the use of surface simulations for doing benefits assessment of ATD-2, and I think Hanbong's talk about SOS it's a good segue into this because we used the SOS simulation platform for this study. I guess other than myself, there are a number of people from ATAC Corporation involved in this research. We also had our collaborators, Professor Hamsa Balakrishnan from MIT and her student Sandeep Badrinath, who is here in the audience. And we also had Mark Rose, Benjamin Levy, and Jamie Cardillo from MCR Federal on our team. So this is a quick outline of my talk. I'll start with the objectives, then go into the methodology that we use, introduce our simulation platform, talk about results, and then kind of get into some of the lessons learned, some of the recent work that we have done that is kind of showing us more about the limitations of these simulations. So the objectives, and I'll try to go fast because I think we have a 10:50 end time here. Basically what we were asked to do is we were asked to estimate the benefits of the ATD-2 system. We were told to do high fidelity simulations at 3 major airports. So we focused on Charlotte, DFW, and Newark for this study. And we were asked to use high fidelity simulations using NASA's SOS simulator, which Han Wong talked about. Other than that, we were also going to extrapolate the benefits that we computed based on these 3 simulations to nationwide results, basically extrapolating them to the FAA Core 30 airports. And then we were asked to compare the ATD-2 costs with the benefits. The methodology that we used, we did a number of different steps to get to the end. We started with identifying a number of operational shortfalls and benefit mechanisms of ATD-2 that can address those shortfalls, and we also developed metrics to measure those benefits. Then we developed a combined airspace surface simulation platform that can simulate the traffic basically from the departure gate to the overhead stream merge point, because I guess the ATD-2, the sphere of influence of ATD-2 spans not just the surface but also the airspace part where departures merge into overhead streams. Once we had the simulation platform, we conducted high fidelity simulations using SOS integrated with the airspace simulation. And we also did a big study for carefully selecting these simulation days, because when you are talking about high fidelity simulations, we are limited to do a small number of simulations. We can't do like thousands of simulations to measure, so carefully selecting simulation days and scenarios was important. Next, we extrapolated the results to the FAA Core 30 airports. We used what we call medium fidelity queuing simulation models to support this. We also extrapolated the results from few simulations to an annualized benefit number. And then we also followed the FAA recommended process for performing cost analysis. And then the way we did our cost benefit analysis is we tried to sort of measure the advantages that the ATD-2 program can provide to the FAA's TFDM program. How does ATD-2 change the benefit cost ratio of the TFDM program basically? So these were the number of components of the work we did. I'm not going to talk about all the components. Han Bong asked me to focus on the simulation part, so I'm just going to talk about the simulations today. But we have a number of conference papers and NASA reports that talk about this. So if you want to learn more about it, I guess contact me. So let me start with the surface simulation platform that we created. Because we basically took the SOS simulation platform that Han Bong talked about, and we added a number of components to SOS to basically to simulate pushback readiness uncertainty, EOBT uncertainty, and we also had to do a lot of work with taxi rerouting because SOS tended to end in these gridlock type of scenarios, so we had to create a lot of algorithms to create realistic taxi rerouting to avoid gridlock situations. Our platform also had a number of other components. I guess the surface part of a departure was simulated by SOS. But once the departure took off from SOS, it entered another simulation which we called AOSS, or the Airspace Operations Simulator and Scheduler. Now AOSS is it's a ATAC simulation. It's a sector-based airspace model. In this model, once the flight departs from the Charlotte surface, it basically transits from the departure runway to the track on, crosses the departure fix, and then enters. It goes through multiple en route sectors, and finally ends at the TBFM metering arc for its destination airport. And for this study, we primarily focused on departures from Charlotte going to the northeast, so going to the DC area airports and New York area airports. And I'll kind of motivate why we need that on the next slide. So this model had all those, the transition model. We had also models for sort of modeling the merging of departures from other airports with Charlotte departure traffic at the departure fix, and also at the en route merge streams. And basically, we used queuing at those merge nodes to estimate airborne delays. Another component of this simulation platform, it basically emulated the existing, the pre-ATD-2 processes for implementing the TMIs like APREX and the edicts because of ground delay programs. So this is the process where I guess the TMC tried to estimate a runway takeoff time, communicated that with the center, and then we also had the other component where the center then fit that flight in the TBFM metering arc timeline, and they communicated back the release time from the runway, which basically mandated a -1 + 2 minute APREC window around that time. We also had, what did I do here? We also had, how do I use the pointer here? Right there. So we also had models where we also kind of model the sequence changes that the ground controllers implement to avoid two departures going to the same meter fix, departure fix, one behind the other. So we had a lot of complexity in this airspace surface simulation platform, and the output from there was basically the simulated surface and airspace trajectory. So this thing modeled the pre-ATD-2 operations. For the post-ATD-2 operations, we also had a detailed model, an emulation of the ATD-2 tactical surface scheduler, which basically interacted with the center timeline. It computed gate holds for APREC flights, gate holds for other flights also, which are not impacted by APREC flights if the demand for the runway exceeded its capacity. So we had a kind of a realistic emulation of how the airport would perform both pre-ATD-2 and post-ATD-2. Here's a quick snapshot of the whole airspace model that we had. As you can see, the Charlotte was the SOS model, but in addition to that, we had also departures coming from, I guess, neighboring airports within the Charlotte track-on. Sometimes they merge with the Charlotte departures at the departure fixes. We also had all the traffic that went to the northeast area airports from all the other parts of the country, and they basically entered the simulation at these simulation injection arcs. And they had, as we analyzed track data, historical track data for those operations, and we created the sector transit time models for them based on that data. And these other departures, they basically occupy slots on the timeline at the TBFM meter arcs. And in our algorithms, the Charlotte departures then, when they call the center for getting their release times, they basically get put into the gaps into those slots that are at these meter arcs. So this was our model. It had kind of the whole purpose there was to be able to model all the benefit mechanisms of ATD-2. So we had the data exchange benefit mechanisms where we modeled EOBTs, uncertain EOBTs, again using the similar models like what Hanbong presented earlier. We also had, as I said before, we had an emulation of the ATD-2 tactical surface scheduler. And as I said before, we used the airspace model to enable emulation of how the integrated airspace scheduling works with ATD-2. So this was all about our simulation platform. I'll next kind of talk a little bit about how we designed the experiment. And I have only one slide on this, but this was a big effort. We spent a lot of time on carefully selecting simulation days. We looked at a number of factors. We looked at TMIs on each day. We did a full year analysis. We looked at the weather over the entire US. We looked at weather around the focus airport, Charlotte, Newark, DFW. And we basically tried to we also looked at demand. So we basically tried to create these groups of similar days based on these different factors. And MCR Federal did this work. They have written a paper about this work. If you're interested, let me know. But kind of to summarize, we basically found that there were kind of 6 different types of days for Charlotte, 6 different types of days for DFW, and 4 types of days for Newark. So we picked one scenario from each of those similar days for each of the airport. So we had 6 Charlotte days, 6 DFW days, 4 Newark days, and then we simulated basically the baseline operations, which is pre-ATD-2 operations for them, and then the ATD-2 operations for them using SOS. So these were basically our high fidelity simulation. That's what we call the SOS simulations. But other than that, our benefit analysis and extrapolation process also involved these queuing models, which MIT has developed. We call them the medium fidelity models. We use the results from our high fidelity simulations to tune these models, basically to see if there were any differences between what SOS is telling us as compared to what the queuing models are telling us. And these we then employed to kind of simulate at more days, because these we only did 6 days, so these we were able to employ them for more days to do a wider estimate of the benefits. I guess MCR Federal and MIT, they were also involved in the TFDM benefit cost analysis, so they leveraged those results and kind of the differences that we saw between the high fidelity and medium fidelity models to kind of create multipliers for the benefit ratios that they found out when they did the TFDM analysis for the core 30 airports. So using this kind of a hybrid approach, we were able to estimate benefits at these 3, Charlotte, Newark, and DFW, but we are also able to estimate kind of what would be the impact at a high level at the other core 30 airports. And once we had that for the simulated days, we then scaled the individual airport benefits, multiplied basically by the number of similar days over the year to get the annualized benefit. And then we converted that into dollar numbers using, I guess, the standard methodology that's usually followed. I just wanted to quickly show what I meant by the medium fidelity models. And Sandeep here would know more about these models. I guess MIT developed them. They developed them for both the baseline, the pre-ATD-2, as well as the ATD-2 operations. Excuse me. And these models basically involve, they have nodes for most of the main areas of the airport, and then there are queues connecting those nodes. And then MIT also did a number of simulations to validate those results with real data, and then the validated models were used in our research. So now I'll talk about some of the results that we obtained. This is the summary of the results that we obtained. I'm showing all the days that we simulated in SOS here, and I'm only showing the full day kind of benefits in terms of taxi out time savings in minutes here. And then this was kind of the average taxi out time per departure that we found out. Now I'm only showing the summary results here in interest of time, but we did very detailed analysis on each of the simulated days. We looked at how the taxi out times look in the ATD-2 operation with respect to the baseline operations. We also looked at the gate delay plus taxi out time. We did find that we were able to reduce the total, I guess, gate delay plus taxi out time in the ATD-2 case for some of the days in our simulations, which was kind of a surprising result for us. But other than that, we also looked at arrivals. Does ATD-2 scheduling had a negative impact on arrivals? Did it have a negative impact on the on-time performance of the airlines? Did it have any negative impact on the airport throughput? And we basically found out no negative impact on those metrics. Then this is basically the way we calculated the benefits. As I said, mostly shifting delays from taxiways to the gates was the main benefit, but we also found out some instances of earlier takeoff time, basically saving the gate delay plus taxi out time for some of the scenarios that we simulated. So we basically used that, and then that gets multiplied by the airline direct operating cost per minute and the passenger value of time, and then basically benefit on individual day multiplied by number of similar days. That's the annualized benefit. Now on the cost side, again, MCR they did an extensive survey of the TFDM work breakdown structure, and they also looked at what ATD-2 was developing, and they found places where the algorithms, the software, the processes that ATD-2 is developing that would reduce the risk in the TFDM program for specific parts of that work breakdown structure. And based on their assessment, I guess the risk parameter in their estimation of the cost can be adjusted downwards. And that led to a decrease of 2.5% in the mode of the cost estimate. That's kind of the metric that they use for estimating the cost of a program. So basically we found out that because ATD-2 has done a lot of groundwork, the FAA might be able to save 2.5% of its TFDM program costs. And then the final economic analysis, basically we were trying to see if ATD-2 would have a beneficial impact on the benefit to cost ratio of the TFDM program. So the benefit to cost ratio of the TFDM program that an earlier study had estimated was 1.03. Based on all our simulations and the benefit calculations, extrapolating them to nationwide, extrapolating them to annualized, we found out that the benefit, we were estimating it would be 1.77 times the benefit that was earlier estimated. And again, I mean, there are a number of assumptions in the simulations that might have led to some overestimation or maybe even underestimation now based on what we have heard in the last few sessions. And again, the costs were reduced by 2.5%. So overall, it led to, I guess, what we are estimating is that because of ATD-2, the benefit cost ratio would improve to, it was 1.03 before, it would improve to 1.89. Next, I'll talk about some conclusions. As our simulation showed, ATD-2 offers, we saw significant taxi out time savings at congested airports, and we didn't see any negative impact on any of the other metrics that we looked at. For just the 3 airports that we simulated, we found out an annual 3.5 million minutes of reduced taxi out time. And overall, I guess all the benefits, they were around $2.6 billion in terms of monetary benefits. And as I said before that, we estimate that it would improve the benefit cost ratio from 1.03 to 1.89. I'll go into some of the lessons learned. I guess as anyone who has done simulations, I mean, model validation is very complex. I mean, here we basically looked at plotted taxi out times, taxi in times against, I guess, the clock time. They did match very well. The departure queues also match very well. We also did like side-to-side playbacks of simulated traffic versus real traffic. When we looked at that, I guess the departure queues really look quite close by. But when you look into the ramp, I guess you can't just, I mean, there is no one-to-one correlation because there is a lot of complexity in the airport operations that cannot always be modeled in a simulation. The second kind of lesson learned is careful selection of simulation timeframes is really important. I'm really glad that we spent so much time really carefully selecting simulation days, because I guess that goes into the third bullet, because of the high fidelity simulations, and we had 3 airports, baseline ATD-2 scenarios for each airport. We knew that we were not able to simulate a large number of scenarios. So I'm really glad that we did a good thorough job at picking the simulation timeframes. But again, since we are limited in the number of scenarios, again, that might play into, because we are recently looking into some of the APREC flights. Does an APREC flight, I think I'm getting the time up, but yeah, this is, I guess, if you have any more questions, I'm glad to take them offline. But I just wanted to quickly show some other examples that Hanbong wanted to show me for use of simulations. We did another NRA for NASA where we did a benefits assessment of a ATD-3 technology called MFCR, and we used Facet to run basically a full year of historical data through those simulations to estimate rerouting in the en route airspace, kind of those types of benefits. We are also currently doing a phase 2 SBIR, Small Business Innovative Research Project, called the NAS Element Closure Planner, where we are using simulation in a what-if analysis kind of a use case. So we're using ATAC SimMod simulation to basically predict, I guess, if you close a part of a runway, basically a runway or a taxiway, I guess what are good time frames for closing them? I guess if you close it now versus later, I guess what delays would you see? Is it good to close now, or is it good to wait until you close it for basically saving delays and causing less congestion? And I think that's my last slide, and I don't know if you have time for questions. Are there any questions online?
Actually, we have one question from online app. Were you able to compare the result for high fidelity models against the medium fidelity models directly to assess their accuracy?
Oh yeah, we did compare the medium fidelity model results with the high fidelity, but the approach that we took is we believed that the high fidelity model was correct. So we basically used that comparison to come up with a multiplication factor. So if SOS predicted 2 minutes of delay savings and queuing model predicted 1 minute, our basically multiplication factor was 2. So we basically used it in that kind of that type of use for the comparison.
You're monitoring time savings with us yearly, the 3.5 billion minutes saved taxi out time, is that per year? My assumption is for the nationwide?
Yeah, the question was the 3.5 million minutes per was that per year? Yes, that was per year. Yeah, Dave.
Hey, that means great work. Just regarding the minutes saved and the dollars, can you, just for expectations management, can you break that down? How much was for taxi savings that was just a reallocation back to the gate versus how much was delay savings that was driving ADOC and PPT? So of your billions of savings, can you just put it into those two?
Sure. I think, I guess the question from Dave was, I guess, can we separate it out? What part of the delay savings was because of taxi delay moving to gate versus saving the total takeoff time?
Saving the total and actually,
Yeah.
reducing overall delay.
Yeah, off the top of my head, I think it was like a 40-60 shares. The 60 being because of the reduced off time. I think the reduced off time.
That's important.
Yeah.
That it's the
You're
way
not-
the simulation is working, a lot of that savings is being driven by what our American colleagues better departure.
And the 40-60 I mentioned, that's in the dollar numbers, because the off time, the ADOC and the PVT, those were like large multipliers. So even 1 minute saved there meant a lot of dollars, versus the fuel saving was just multiplied by the cost of fuel per minute.
Okay, so if you have more questions, you can use the break time. So thank you for attending our session. And 8-minute break time, we will gather to the Texas Learning Center, the big conference room, to gather your valuable input about the NASA's future plan. Thank you.